Roughly 13.8 billion years ago, the universe as we know it expanded from an infinitely hot and dense singularity in space and time, first in a furious torrent of rapid cosmic inflation for a fraction of a second, and then in a more calm manner we see today, gradual yet accelerating expansion fueled by dark energy. This fleeting expansion describes the Big Bang model of cosmology, the most successful theoretical explanation for our grand universe. Backed by boatloads of observational evidence, we can be very sure of its veracity. Caltech astrophysicist Sean Caroll even described the Big Bang as, quote, 100% true. And now, in a breathtaking colossal celestial discovery, astronomers have discovered the first bubble of galaxies, an almost unimaginably huge cosmic structure thought to be a fossilized remnant from just after the Big Bang sitting in our galactic backyard started. The existence of the billion light-years-wide cosmic bubble has attracted the attention of the whole science community as it has helped us unlock the mysteries of early galaxy evolution. But the finding also left scientists scratching their heads, as it provides a clear picture of the universe that could revolutionize cosmology. Join us today as we dig deep into scientists' new discovery of an enormous cosmic bubble, challenging our understanding of the cosmos. In a stunning revelation, astronomers have just reported that they discovered an enormous cosmic bubble packed with galaxies that stretches nearly 1 billion light-years across, or 10,000 times wider than the Milky Way galaxy. And it seems to be an accident vestige from the infant universe. Named Ho'olelana, a nod to a Hawaiian creation chant that describes the origin of structure, the massive bubble is thought to be what's called a baryon acoustic oscillation, or BAO. These fossilized imprints of matter in the early universe date back more than 13 billion years ago, to the moment the cosmos entered a new transparent phase some 380,000 years after the Big Bang. Ho'olelana, which is located just 820 million light-years from the Milky Way, consists of a full spherical shell of galaxies with a supercluster core, as predicted by theory. The massive bubble also displays an enhanced density of galaxies emanating from its center, and it is composed of previously identified structures that themselves are some of the largest known structures in the universe. The new finding, published September the 5th in the Astrophysical Journal, will not only help astronomers untangle the mysteries of the early galaxy evolution, but also might hint at subtle issues concerning the expansion rate of the universe. Massive BAOs like Ho'olelana are predicted based on their current understanding of the Big Bang and how the early universe evolved. For about 400,000 years following the Big Bang, matter in the universe took the form of a dense, nearly uniform sea of extremely hot plasma, with electrons too energized to settle down with atomic nuclei. Slight density fluctuations of roughly 1 part in 100,000 within this sea led to gravity attempting to pull together larger pockets of matter. However, the universe remained too hot for particles to cling together after colliding, leading to a tug-of-war, if you will, between the outward pressure of radiation and the inward pull of gravity. This created pressure oscillations similar to sound waves in the plasma sea. BAOs were created when these pressure oscillations rippled outward, leading to slight overdensities of matter. But then, some 380,000 years after the Big Bang, the universe cooled to the point that the sea of electrons and nuclei combined into neutral atoms, making the cosmos transparent to radiation. At that point, the bubbles became frozen in place, with any matter density peaks eventually manifesting as vast bubbles that are densely populated with galaxies. By observing and analyzing patterns in galaxy distribution within BAOs, astronomers can learn a great deal about what gave rise to the largest cosmic structures in the universe. The first hints of Ho'olelana were uncovered in 2016 by the Sloan Digital Sky Survey, which captured part of its shell structure. However, that shell was never linked to a BAO, as the true extent of the billion light-year-wide bubble remained hidden. As Brent Tully, an astronomer from the University of Hawaii and lead author of the new study, said in a press release, "We were not looking for it. It is so huge that it spills to the edges of the sector of the sky that we were analyzing." Using data from Cosmic Flows 4, the largest ever compilation of precise galaxy distance, the researchers mapped out the gargantuan bubble in 3 dimensions, allowing them to discern Ho'olelana's full spherical shell, as well as unraveling how its many galaxies are clustered together. According to co-author Daniel Pomerode of CEA Paris-Saclay University in France, who refers to himself as the cartographer of the group, constructing this map, he said, and observing the vast shell structure was an awe-inspiring process. Mapping Ho'olelana in 3 dimensions helps us understand its content and relationship with its surrounding. It was an amazing process to construct this map and see how the giant shell structure of Ho'olelana is composed of elements that were identified in the past as being themselves some of the largest structures of the universe, Daniel Pomerode said. Some of the previously identified enormous structures that are now linked to Ho'olelana include the Sloan Great Wall, the Hercules Complex, the Coma Great Wall, the Bootes Supercluster near the core of the bubble, and the expanse of Bootes Void, which is a roughly 400 million light-year-wide spherical underdensity of galaxies. The discovery of Ho'olelana might have more profound implications than just a better understanding of the hierarchy of nearby galaxy superstructures too. In a shocking revelation, scientists have just unveiled that the enormity and proximity of Ho'olelana raises questions about the presumed expansion rate of the universe. As Tully said, the very large diameter of 1 billion light-years is beyond theoretical expectations. If its formation and evolution are in accordance with theory, this BAO is closer than anticipated, implying a high value for the expansion rate of the universe. In other words, the existence of the billion light-years wide cosmic bubble may further complicate the already contentious issue and question of how fast the universe is really expanding. In 1929, Edwin Hubble discovered that galaxies are moving away from us at speeds proportional to their distances. It helps to think about the universe like a balloon being blown up. As the stars and galaxies, like dots on a balloon's surface, move apart from each other more quickly, the greater the distance is between them. That means the further away a galaxy is from us, the faster it is receding. This provided the first clear evidence that our universe is expanding. Ever since this discovery, the current rate of expansion, or the Hubble constant, has been one of the key properties of our universe that cosmologists study. Unfortunately, the Hubble constant has long been difficult to measure. The more astronomers measure this number, the more it seems to defy predictions built on our understanding of the universe. One method of measuring it directly gives us a certain value, while another measurement, which relies on our understanding of other parameters about the universe, says something completely different. Either the measurements are wrong, or there is something flawed about the way we think about our universe and how it works. But scientists now believe that they are close to an answer, largely thanks to the new experiments and observations aimed at finding out exactly what the Hubble constant really is. What faces us as cosmologists is an engineering challenge. How do we measure this quantity as precisely and accurately as possible, says Rachel Beaton, an astronomer working at Princeton University. To meet this challenge, Beaton says, requires not only acquiring the data to measure it, but cross-checking the measurements in as many ways as possible. From my perspective as a scientist, she says, this feels more like putting together a puzzle than being inside of an Agatha Christie-style mystery. The first ever measurement of the Hubble constant in 1929, by the astronomer whose name it carries, Edwin Hubble, put it at 500 kilometers per second per megaparsec, or about 310 miles per second per megaparsec. This value means that for every megaparsec, a unit of distance equivalent to about 3.26 million light-years, further away from Earth you look, the galaxies you see are hurtling away from us at 500 kilometers per second, or again 310 miles per second, faster than those a megaparsec closer. Over a century since Hubble's first estimate for a rate of cosmic expansion, that number has been revised downwards time and time again. Today's estimates put it somewhere between 67 and 74 kilometers per second per megaparsec, and that's about 42 to 46 miles per second per megaparsec. Part of the problem is that the Hubble constant can be different depending on how you measure it. Most descriptions of the Hubble constant discrepancy say that there are two ways of measuring its value. One looks at how fast nearby galaxies are moving away from us, while the second uses the cosmic microwave background, or CMB, the first light that escaped after the Big Bang. We can still see this light today, but because of the distant parts of the universe zooming away from us, the light has been stretched into radio waves. These radio wave signals, first discovered by accident in the 1960s, gave us the earliest possible insight into what the universe looked like. Two competing forces, the pull of gravity and the outward push of radiation, played a cosmic tug-of-war with the universe in its infancy, which created disturbances that can still be seen within the cosmic microwave background as different tiny differences in temperature. Using these disturbances, it is then possible to measure how fast the universe was expanding shortly after the Big Bang, and this can help then be applied to the standard model of cosmology to infer the expansion rate today. This standard model is one of the best explanations we have for how the universe began, what it is made of, and what we see all around us today. But there is a problem. When astronomers try to measure the Hubble constant by looking at how nearby galaxies are moving away from us, they get a different figure. The European Space Agency, or ESA's Planck satellite measured discrepancies in the CMB, first in 2014 and then again in 2018, and the value that came out for the Hubble constant, 67.4 kilometers, or 41.9 miles per second per megaparsec. But this is around 9% less than the value astronomers like Wendy Friedman, an astrophysicist at the University of Chicago, have measured when looking at nearby galaxies. Further measurements of the CMB in 2020 using the Atacama cosmology telescope correlated with the data from the Planck. This helps to rule out that there was a systematic problem with Planck from a couple of sources, says Beaton. If the CMB measurements were correct, it left one of two possibilities. Either the techniques using light from nearby galaxies were off, or the standard model of cosmology needs to be changed. The technique used by Friedman and her colleagues takes advantage of a specific type of star called the Cepheid variable. Discovered around 100 years ago by an astronomer called Henrietta Leavitt, these stars change their brightness, pulsing fainter and brighter over days or weeks. Leavitt discovered the brighter the star is, the longer it takes to brighten, then dim, and then brighten again. Now astronomers can tell exactly how bright a star really is by studying these pulses in brightness. By measuring how bright it appears to us on Earth, and knowing light dims as a function of distance, it provides a precise way of measuring the distance to stars. Friedman and her team were the first to use the Cepheid variables in neighboring galaxies to our own to measure the Hubble constant using data from the Hubble Space Telescope. In 2001, they measured it at 72 kilometers or 45 miles per second per megaparsec. Since then, the value from studying local galaxies has hovered around the same point. Using the same type of stars, another team used the Hubble Space Telescope in 2019 to arrive at a figure of 74 kilometers or 46 seconds per megaparsec. And then, just a few months later, another group of astrophysicists used a different technique involving the light coming from quasars to get a value of 73 kilometers or 45 miles per second per megaparsec. And most recently, as astronomers unearthed billion light-years wide cosmic bubbles situated right in the Milky Way's backyard like they have, Hubble trouble could deepen. Specifically, according to the new study's analysis of Ho'olelana as a BAO, the researchers calculated a slightly faster expansion rate of between 74.7 and 76.9 kilometers per second per megaparsec. If these measurements are correct, then it suggests that the universe might be inflating faster than theories under the standard model of cosmology allow. It could mean this model, and with it our best attempt at describing the fundamental nature of the universe, needs to be updated. At present, the answer is not certain, but if it proves to be the case, then the implications could be profound. It could be telling us something is missing from what we think is our standard model, says Friedman. We don't even know the reason why this is happening, but it's an opportunity for a discovery, she says. If the standard model is wrong, one thing it could mean is our models of what the universe is made up of, the relative amounts of baryonic or normal matter, dark energy, and radiation, are not quite right. And if the universe is really expanding faster than we thought, it could be much younger than the currently accepted 13.8 billion years. An alternative explanation for the discrepancy is the part of the universe we live in is somehow different or special compared to the rest of the universe, and that the difference is distorting the measurements. It is far from a perfect analogy, but you can think about how the speed or acceleration of your car is modified if you go up or down a hill, even if you are applying the same pressure to the gas pedal, says Beaton. I think it is unlikely to be the ultimate cause of the discrepancy in the Hubble constant that we see, but I also think it is important to not disregard the work put into those results. But astronomers think they are getting close to pinpointing what the Hubble constant is, and which of the measurements is correct. As Wendy Friedman, the astrophysicist at the University of Chicago, who has spent her career measuring it, said, "What's exciting is I think we really will resolve this in fairly short order, within a year or 2 or 3. There are so many things that are coming on the horizon that will improve the accuracy with which we can make these measurements that I think we will get to the bottom of this," she confidently said. One of the ESA Space Observatory, Gaia, which launched in 2013 and has been measuring the positions of around 1 billion stars to a high degree of accuracy, scientists are using this to work out the distances to the stars with a technique called parallax. As Gaia orbits the Sun, its vantage point in space changes, much like if you close one eye and look at an object, then look with the other eye at it and it appears in a slightly different place. So, by studying objects at different times of the year during its orbit, Gaia will enable scientists to accurately work out how fast stars are moving away from our solar system. Another facility that will help answer the question of what the Hubble constant's value is the James Webb Space Telescope, or JWST, which was launched in late 2021. By studying infrared wavelengths, the JWST allows us to better measure what won't be obscured by the dust between us and the stars. If they find the difference in the Hubble constant does persist, however, then it will be time for new physics completely. And although many theories have been offered up to explain the difference, nothing quite fits what we see around us. Each potential theory has a downside. For example, it might be that there was another kind of radiation in the early universe, but we have measured the CMB so accurately that this does not seem likely. Another option is that dark energy could be changing with time. That looked like a promising avenue to pursue, but now there are other constraints on how much the dark energy could change as a function of time, says Friedman. You'd have to do it in a really contrived way, and that doesn't look very promising, she said. An alternative is that there was dark energy present in the early universe that just disappeared, but there is no obvious reason why it would do this. It has forced scientists to dream up new ideas that could explain what is going on for sure. People are working hard at it, and it's exciting, adds Freeman. Just because no one's realized what the explanation is yet doesn't mean that there won't be a good idea that will emerge eventually, she said. Thus, most likely, we may be on a significant precipice of scientific history, similar to what we experienced in 1904. At that time in 1904, physics had never before seemed to be on such solid footing. For more than 2 centuries, the principles of Newtonian physics had been applied successfully to problem after problem. And although physics expanded their knowledge, into areas such as electricity, magnetism, and heat, these aspects of the world were not really so different from those Newton had described hundreds of years earlier. To the physicists of 1904, the world seemed, well, understood. There was little reason to expect a revolution. Similar to the situation cosmologists confront today, however, the physicists of 1904 had not yet been able to address a few challenges. The medium through which they believed light traveled, the luminiferous ether, should have induced variations in the speed of light, and yet light always moves through space at the same rate. Astronomers observed the orbit of Mercury to be slightly different from what Newtonian physics predicted, leading some to suggest that an unknown planet dubbed Vulcan might be perturbing Mercury's trajectory. Physicists in 1904 had no idea what powered the sun. No known chemical or mechanical process could possibly generate so much energy over such a long time. Lastly, scientists knew various chemical elements emitted and absorbed light with specific patterns, none of which physicists had the slightest idea of how to explain. In other words, the inner workings of the atom remained a total and utter mystery in 1904. Although few saw it coming, in hindsight, it's clear that these problems were heralds of a revolution in physics. And in 1905, the revolution arrived, ushered in by a young Albert Einstein and his new theory of relativity. We now know that the luminiferous ether does not exist, and that there is no planet called Vulcan. Instead, these fictions were symptoms of the underlying failure of Newtonian physics. Relativity beautifully solved and explained each of these mysteries without any need for new substances or planets. Furthermore, when scientists combined relativity with the new theory of quantum physics, it became possible to explain the sun's longevity as well as the inner workings of atoms. These new theories even opened doors to new and previously unimagined lines of inquiry, including that of cosmology itself. Scientific revolutions can profoundly transform how we see and understand our world. But radical change is never easy to see coming. There's probably no way to tell whether the mysteries faced by cosmologists today are the signs of an imminent scientific revolution or merely the last few loose ends of an incredibly successful scientific endeavor. There's no question that we have made incredible progress in understanding our universe, its history, and its origin, but it is also undeniable that we are profoundly puzzled, especially when it comes to the earliest moments of cosmic history. We have no doubt that these moments hold incredible secrets, and perhaps the keys to a new scientific revolution. But our universe holds its secrets closely, and it's up to us to coax those secrets from its grip, transforming them from mystery into discovery. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. And as always, thanks for watching, and we'll see you next time.